So in this video, we are finishing up our discussion of section 8.1 on sequences, and we are going to use the squeeze theorem in this example. Now, the squeeze theorem for sequences is stated pretty much the same as the squeeze theorem for functions, except now we're talking about sequences instead of functions. So we need to have two sequences that are less than or equal to our given sequence and greater than or equal to our given sequence. And we also need the limits of these two sequences, AN and CN, to be the same thing. If that is true, then they will end up squeezing BN together. So this means that the limit as n goes to infinity of Bn is also going to equal L. So in this case, Bn is the given sequence. Even if this isn't always labeled as a Bn, just remember that Bn for the squeeze theorem is the given sequence. So you need to find a sequence that's a little bit less than or equal to and a sequence that's a little bit greater than or equal to. And the way that we're going to do this is by using the fact that the cosine function is always between -1 and 1. Now this is true even for the continuous cosine function, so it'll definitely be true if if we only consider plugging in integer values into our cosine function. Well, since the cosine of n is between -1 and n, or -1 and 1, if we divide that by n minus 1, notice that n is bigger than or equal to 1 or possibly 0. Now, let's say n is bigger than or equal to 1. So then n minus 1 is going to be bigger than or equal to 0. And in fact, we should, in order to make sure that our first term is defined, we would probably say that n is bigger than or equal to 2 to make n minus 1 defined. Or, sorry, to make n minus 1 non-zero. So we can divide by it. So this means that n minus 1 is going to be bigger than or equal to 1, which is strictly greater than 0. So the reason why that's important is if you divide through with an inequality by a positive number, it doesn't change the signs. So we divide through by n minus 1. We have -1 is less than n minus 1. Is less than -1 over n minus 1. Sorry, I'm not using the right words right now. -1 over n minus 1 is less than or equal to cosine of n over n minus 1 is less than or equal to 1 over n minus 1. Notice what we have in the middle here is the given sequence. So this would probably be a good choice for AN, and this would be a good choice for CN. Okay, so we need to figure out what the limits of those two sequences are. -1 over n minus 1 and the limit as n goes to infinity of 1 over n minus 1. Well, the numerator is a constant in both of these. It's a different constant, but it's a constant. The denominator is going to infinity. So if that ever happens, a constant over infinity, it doesn't matter what the constant is, the whole thing is going to go to 0. So both of these sequences are 0. Notice that this is equal to the same thing, like what we have here. They're both equal to L. So this then means that the limit of the sequence that we've been given, which is, the cosine of n over n minus 1 is going to equal L, which is 0 in this case. And that is our final answer. This is how we use the squeeze theorem for sequences. Remember, you need to find a sequence that's a little bit below and then another one that's a little bit above. Both of those sequences need to have the same limit value. If they don't have the same limit value, it doesn't mean anything about your sequence, okay? That is the downside of using the squeeze theorem. It's a one-directional theorem. It's an if-then statement. So if the beginning of the statement, the if part, is that if that is not true, you can't come to any sort of conclusion about the other limit, okay? This is one-directional. You have to have all of this stuff be true, and then you can come to your conclusion. If any one of these things is not true, you simply just can't come to a conclusion. But in this case, we've used the fact that the cosine is bounded to get a couple of bounding sequences. They both have the same value, so we get our limit of the given sequence is the same thing.